Welcome to SQVe Structural Summit. We are very much thankful of you for participation in the live discussions. Please subscribe to our YouTube channel of SQVe Academy and press on the bell icon. You will receive notification for the future events when we go live. Also, kindly like and share the video with the engineers in your network so that more numbers of engineers may be benefited. We are planning to come up with more and more important and informative videos. To support the initiative, you may join our YouTube channel of SQVe Academy with nominal monthly subscription. In return, you will get access to member-only videos at YouTube and the other perks. The subscription can be cancelled at any time. Step-by-step approach to join the YouTube channel is mentioned on the screen. For any doubts, you may get in touch with us through email address. Thank you.
Hello, welcome Nandip Goelji. Yeah.
Hello, sir. How are you?
Yes, I'm absolutely fine.
Okay, so hello everyone.
Yeah. So when we just floated this event in the social media, in fact, we have received so many questions, right, for the bridge engineering. And before we start, could you please quickly introduce yourself, to the audience?
Sure. So hi everyone. I am Nandip Gohil. I am MTech in Structural Engineering. I did my master's from NIT Surat, and I have been working as a bridge design engineer for about 12 years. So I was with Jacobs for about 2 years, and then for past 10 years, I have been associated with MIDAS, where I'm mainly assisting our clients in their technical doubts pertaining to, not just the software, but even the engineering related doubts for different types of bridges all around the world.
Right, great. So we were just wondering, like, could we start, this kind of a series for bridge engineering, wherein we can take up interesting questions from the audience, and then we can have open discussions on them. It may be based on, let's say, in form of PPT, or let's say maybe in form of some software applications. Right? So this is just first, pilot session which we are planning, and based on the interest of the audience, we were trying to plan a number of more sessions in the future. Right.
Perfect. Yeah. And that's actually a good idea. There's a bit of knowledge gap in this aspect, so this would definitely be good.
Right. So now you can share your screen and we can start.
Perfect.
Yeah. So meanwhile, just for the audience, we are live on the YouTube, Facebook, as well as on the LinkedIn, and you'll be able to interact with us through the live chat. So please feel free to mention the discussion points, queries, etc. as we progress in the session, and we'll collate those points, and then we will discuss the same towards the end of the session. Yeah, so your screen is visible. Yeah, you can start.
Okay, perfect. So I'll get started. So once again, good evening, everyone. Today I'll be presenting about bridge engineering applications with the usage of MIDAS software packages. For today, as I said, we'll just focus on bridges. So the 4 softwares that we have for that are Civil, CIM, CAD, and FEA. So let's get started. So this will be the flow of the presentation. I have received a lot of questions. I have shortlisted about 14 of those right now.
Just one, small interruption. Could you please click on the hide button on your screen?
This one.
Yeah, so that logo will go.
Yeah.
Okay.
Perfect.
Thank you.
Okay, sure. So I have received a lot of questions. I have shortlisted about 14 of those for now, considering the area of audience that we would be having. And I've broadly classified it into these categories. So let's get started with the first one. So I'll just give you guys a brief introduction about the software, the company, and what we have been doing. So we started out in 1989, and we were an engineering software development as well as consulting company. So all the engineers that we have who are developing the software, believe it or not, they do code well, but they are all structural or mechanical engineers, not computer engineers. Okay, so we have about 800 employees and over 200 developers. Recently, we actually moved out of consulting part because the demand for the software development aspect was so high that we couldn't, just feasibly continue with the consulting aspect. So we have a large bucket of softwares, but I'll just focus on the four main categories right now. So for bridges, as I mentioned before, these are the four softwares that we have: Civil, CIM, CAT, and FEA. For geotechnical analysis, where you can go for your slope stability, foundation, excavation, and whatnot. So for all of those, we have GTSNX, SoilWorks, or GeoXT. Similarly, for buildings, we have Design Plus, Engine, and Gen. And similarly, we have a few softwares for mechanical domain. So coming to the next part, yes, there is a bit of interest, and that's one of the reason why we are having this session as well. People want to know how or where they can learn the softwares. So one of the ways is this. Okay, so we actually have a dedicated Academy website, and for all of you who have logged in or are having a look at this video, we'll definitely give you access to the website to all the courses, so you could try those out. No doubt, you'd be having those as lifetime access, right? So moving on now, coming to the questions aspect. So one of the common questions that I had would fall in this category. So what are the prerequisites to actually use a software? And this is personally, I would say, one of the most important categories. So these are the questions. As a student, what I should focus on. As a designer, similar thing. Um, how accurate is the analysis result provided by the software? And is the software enough for analysis, or do we need to go for further manual calculation? So let's get started with the first question. So as a student who has just started learning about bridge design, one of the basic things that you need to do is you need to focus on what new things you need to learn for the bridge as compared to buildings. So the unique loading conditions, the vehicular loads, temperature gradient loads, pre-stressing loads, time dependent effects, what all unique loadings would be acting on structure, and what would be the effect of it. That brings you to the next point, the structural behavior. It is of paramount importance to completely understand how a structure is behaving. Yes, no one will expect you to completely understand 100% behavior of a very complex structure, but simplified things, whether the deformations are as expected or not. Like for a symmetric structure with symmetric loading, you should not be having a transverse deformation. So these kind of common sense rough check kind of uh, understanding of a structural behavior is a must. So try to understand those things as well. Then simplifications and assumptions. See, as an engineer, we decide how much we want to simplify a problem. If you want to analyze a cable stayed bridge, it is your decision to model the complete structure with line or plate elements. It's your decision whether you want to model the bearings or you want to model those directly as fixed connectivity. Assumptions are a must because one, that helps us in understanding what kind of behavior a structure would be having, and two, it simplifies the process of coming to the final design forces. That brings me to design guidelines. For buildings, we have IS codes. For road bridges, while this may not be covered in institutes, but for road bridges, we have a code which is IRC code, Indian Road Congress codes. Similarly, for railways, we have IRS codes. So there are different codes out there, and this is a bit funny part, but the modulus of elasticity of M40 grade of concrete is different for all of these codes, though it's the same M40 grade of concrete. So that's there. But anyway, so you should be having knowledge of all of these codes. What are the design guidelines? What checks you should be going? Your ultimate serviceability, stability checks for flexure, shear, torsion, and so on. So you should be aware of what all you need to check for your structure. Now, if I am to say one very simple thing, when it comes to a building or steel structure, usually there is a deflection check. For bridges, surprisingly, there won't be. So there, the serviceability checks for bridges usually spans to your crack width checks and your stress checks. Okay, so you should be knowing about these things. And the last point, which is coding knowledge. Okay, so all of the things that we talked about until this point, they had to do with structural engineering, behavior, things you need to know as a bridge design engineer. The next part, the coding knowledge, that's completely optional. Now, when I say coding knowledge, Excel is the basics of the basic. You should know what different kind of commands you can use in Excel to make your life easy. That includes stuff like match, offset, index, and so on. You should be aware of that. If you don't know that, you should look for a course like this on Excel and you should go through that. Next part, which is again optional, is the VBA coding or Python coding. Now, you may have a question like, hey, I'm a structural engineer. Why should I get into all that part? That will make your life a lot easier. Something that takes you 1 week to do manually, if you learn coding, you can do that within a couple of minutes. That improves your productivity. That brings you in the eye of your employer, so to say, or if you plan to start your own business, that gives you the edge of delivering the projects quickly to your client, leading to more profitability. At the end of the day, if you want to rise above the rest of the crowd, you need to do something that most of the others are not doing, and that part is coding knowledge. All the structural engineers would definitely be studying about structural engineering. Few of them would have interest in coding and would be doing that. Believe me, you should not ignore the knowledge in structural engineering, but having this additional aspect of coding definitely helps out. Okay, coming to the next aspect. So as a designer, what should you know? Irrespective of the software, you should have a thorough knowledge of what the default options or the basic algorithms of the software are. How is the self-feed being considered for, say, eigenvalue analysis? Is it lumped? Is it consistent? How are the support conditions being considered? Is it compression only, or is it linear support, non-linear support? So these are the basic things. How are the tapered section properties being considered? How is the effective section being considered in case of a pre-stressed section, right? When you start working on any software, to know whether the software is working based on your understanding, the next thing that you do is you simulate using verification problems. So you already have your manual calculations with you for those simplified problems. You replicate the same in the software, and if you get the same results, at least the assumptions that you have about the default options in the software would be true. Next is the strengths and limitations of the design feature. Okay, so for example, okay, let's talk about MIDAS Civil itself. Okay, so when it's a specialized software for bridge design. So when I say that, you can still model any sort of structure in MIDAS Civil. But if you want to design it with, say, IS code, which is for buildings, you can't do that over here. So you need to understand what these limitations are. Yes, analysis is fine. The design is not possible. Similarly, if you want to go for detailed design for any D region, say, for example, a corbel or something like that, or if you want to go for detailed analysis of diaphragm location where the blister is connected or where the cable is ending in a bridge. So these are high stress concentration regions. You should not be using a tool for global analysis like Civil for that, but you should be using a different tool, which is say FEA. So these kind of understanding of a software are a must before you start working on any software. And obviously the final outcome that is required is also a must. So if your final outcome required is of an information model, then your workflow can be very different as compared to starting from Civil. Okay. So Mr. Bhavin, if there are any questions or comments pertaining to the questions that we are covering, just let me know and we could discuss a bit on those as well. Okay.
Yeah, definitely, definitely. If any interesting points are coming up, I'll share it across.
Perfect. Perfect. Okay. So moving on. Now, this is one of the common questions that we get. How accurate is the analysis result provided by the software? See, honestly speaking, all the softwares out there right now, they have had a level of, quality checks, and I can definitely say the results that you would be getting from this software are completely dependent on what you are putting in the software. If for a simply supported beam, you are not getting the bending moment at the mid as WL square by 8, that means something is wrong with the software. And any software that you get out there in the market, which is known, will give you that moment. And in that situation, you can say the software is 100% accurate. Okay. At the same time, if you are doing, say, a nonlinear analysis, okay, and the nonlinear analysis algorithm in different softwares can be different. As a result of that, softwares may all give you different answers to the same problem, but those answers would generally be in the same ballpark figure. Okay, so if something is deviating greatly from that, then something is wrong, and there are very high chances it's not the mistake of the software, it's the mistake of our understanding of the software or mistake in the inputs which are provided. Hence the first point, always remember, garbage in, garbage out. Accuracy of the software does not depend only of the software, it depends on how you are using the software. Okay, next is an interesting aspect. So when it comes to finite element modeling, as if you have gone through that course, you would know that there are different types of finite elements: beams, shells, solid, plane stress, plane strain, and so on, a lot. So how these all elements work is different. Initially I had talked about, simplification and the assumptions. So if I'm modeling, a wide sort of slab kind of structure as a beam element, my cross section is always going to be considered as rigid. The plane section remains plane before and after bending. That thing will be true for that particular beam model. If I'm modeling the same thing as shell, depending on the support conditions, something known as shear lag will come into play. Okay. Now, what is shear lag is a different topic altogether. I would personally recommend, searching for it, going through that, and you'll understand, what basically that would mean. And finally, solid. So in solid, how that distribution of force is happening even across the depth, that is something that you can understand. Okay. As I said, if it's a determinate structure that you are modeling with any of these kind of elements, you should be getting same result. Obviously, you would be getting the same results. But if it is a structure in which these kind of assumptions come into play, so your assumption for a beam, it is not actually valid for a structure which is modeled as a shell. And if the shell represents that structure more accurately, your results would be different. Okay. Again, in this case, it's not the software that is wrong, or it's not one of the method which is wrong. It's purely your assumption. And both answers are 100% accurate if your assumptions are the same as your modeling philosophy. Okay. Next is something known as mesh sensitivity analysis. So when it comes to finite element, again, the size of the mesh, the aspect ratio of the mesh, it would kind of affect how the solution is converging. And you may need to try different mesh size until your variation from the answer is very minimal. Again, that is also a vast topic, something that could be taken 1.5 hours for. But if I am to put it, in generalized terms, if you are having certain localized analysis which needs to get done, you can go for finer mesh in that region. And for a region which is not of interest, you can go for coarser mesh. But again, there are certain rules which need to be followed about the aspect ratio and the shape of the mesh. So that is something that needs to be taken care of. Next, is software enough for analysis or do we have to go for more manual calculations? So this highly depends on your required output. So if, for example, you just want to go for the capacity or the demand calculation, yes, you can apply all your loads, you can check that as an output and you are done. But if you want to, if I'm talking about bridge, if you want to go for something like bearing design, so the software can give you the forces in the bearing, right? Then there are bearing manufacturers out there who tell you, okay, that if this is the force, this could be the size of the bearing. And for that as well, you need to do certain manual calculations. Now that has nothing to do with the force distribution in the software or how, your physically, how your structure is going to behave. So you can take or you need to take these kind of output from the software and you need to do rest of the calculation to arrive at your actual bearing that you want to utilize in the structure, right? So it completely depends on what you want as an output. If you're working on, say, the pre-bid part of a project, you may not need to go into that much detail. But if you're working into detailed design, you may need to go there. Then the software capability. If I am working on a software that only has the capability to go for linear analysis, and if my problem is non-linear, then I need to go for certain manual calculations. Honestly speaking, in today's time when software and systems are easily accessible, we have become highly reliant on softwares. Uh, if I'm being very honest, you should not be using a software unless you are sure of the manual ways of getting things done. So if I'm to put an extreme example, the Golden Gate Bridge in San Francisco, right? It was designed somewhere in the 30s, and the complete calculation obviously happened by hand. In today's time, we don't have that luxury to do the complete calculation on hand, but we still have the time, and frankly speaking, I would say conscious to at least verify the cable forces for one simple cable on which a load is applied. This is something that you can very easily verify manually, and you can check that the software is giving you similar output. So you need to understand what the capabilities of the software are, and then you need to move ahead. Next is a sense of responsibility. The software can be very, very advanced. It can do a lot of things for you. But if you'll read the fine print, all the software will always say that the final responsibility of the outcome is on the design engineer who is using the software, right? At the end of the day, it's a design engineer who is getting the consulting, who is getting the project, who is getting the salary for getting things done. And frankly speaking, that is for the responsibility that you take. Now, if you are completely sure of the quality of the things that you have given in the software, your input and the output that you are getting, great. But no matter how good an engineer you are, somewhere, some things should always be verified manually to ensure you have not made any mistake. Okay. And excuse like, hey, I don't have time for that is not good enough when a bridge fails. So please be very careful about that part. Okay, now let's talk about the design phases of a bridge. Okay, so the first question, how to design a major bridge, it's very vast question. For now, I have just covered what the different phases could be, and then we'll discuss on that. Next is how to assign different boundary conditions, loading, how to determine the tendon profile coordinates, how to assign and verify the time-dependent properties, and how to simulate the composite behavior of a eye girder. Okay, so how to design a major bridge? So if I am to put it in a very generalized term, it consists of four, layers, so to say. So first is the conceptual design phase, where you'd just be readying a few proposals based on the known alignment of the structure. Next is the preliminary design phase. So once the conceptual design of different bridge schemes is ready, you would select one or two schemes which look feasible, and then you'll go for further calculations in that, for quantity, cost, and so on. Next is the detailed design phase. So once the preliminary design is done and one option is finalized, you go for complete calculations. So your demand, capacity, drawings, and so on. And final is the construction design phase. So yes, the bridge is designed. We know how it should finally look like, but how to construct such that the bridge reaches that phase, that is something that you do in the construction design phase. So let's have a look at few of these. So as I said, the conceptual design phase is you ready different proposals based on the required alignment. So in this case, as you can see, an extra dosed bridge, well-end cantilever bridge, a simple girder bridge, and suspension bridge, and two different options for a cable stayed bridge are prepared. Frankly speaking, when it comes to the conceptual design phase, it is not something that takes long, especially with a tool like CIM, where it's basically a bridge information modeling tool. So you just import the ground layout from, say, Google Earth or something like that, and you can use the inbuilt templates to directly place the bridges over there. So this makes it very easy to understand and show to the client, like, okay, so these are the options that we have come up with. Now, which one would you like us to proceed with? So once it is known which option to go for, we come into the preliminary design phase. So in that situation, you need to work out the quantities, the costs, and so on. So you can go for this sort of detailed modeling again, which could be library based. So you just pull that in, you extract the quantity takeoffs, you put on the different bill of the materials, and then based on the schedule of rates, you can work out the final quantity of the final cost of the project which is finalized. Next is the detailed design phase. So you take this preliminary model to say MIDAS Civil for complete analysis, the demand, and you work out the capacities, and you are done with the detailed design phase. And finally, the construction phase. So when it comes to construction, a few of the things are you need to submit the report, and the most important is the good for construction drawings, as well as drawings like these for checks when you are executing it on the site. So knowing the 3D locations to ensure construction is going as expected, things like camber, all of those could be done using a tool like MIDAS CAD. Okay, moving on, next part is the assignment of boundaries and loads to a bridge. So when it comes to boundaries, it's not just the support at the base of the bridge, but even the bridge bearings are a type of boundary condition. Then the substructure modeling, its effect. One of the very common things is the superstructure and substructure are modeled separately in a bridge. So we'll have a look at what effects it can have. Then soil structure interaction and the different loading requirements. So when it comes to bridge bearing, if I'm to broadly classify it into the categories, these are pin bearings, so which is restraining all deformations but no rotation. Guided bearings, so which allow movement in any one direction, and free bearing, which allow movement in all the directions. Okay, so what you are seeing on your screen right now, this is basically a plan view of a two-span continuous bridge supported on piers. So the gray part, the light gray part that you see, that is the bridge deck. The dotted dark gray part that you see, those are the pier caps. And on those, what you see, those are the bearings. So at the center, I have placed, center towards the edge, I have placed the pin bearing. So it is restraining all deformations. Okay. Now, how to decide the placement of other bearings? So one of the basic understanding for this part is, again, this requires a bit of behavior, structural behavior understanding. So if the location of the pin bearing is heating up, that would basically lead to expansion of the structure. So in which direction the structure is expanding, that helps you in understanding what bearing should be placed at that location. So if I am heating up over here, let me just take a pen. Yeah. So if I am heating up this point, okay, then obviously my bridge would expand in this direction, this direction, this direction, this direction, this direction. Okay. So this is how my bridge expansion would happen. So to allow for this movement to happen freely, we will have to put transversely guided bearing on the same pier as the pin bearing, longitudinally guided bearing at the same location where the pin bearing is placed on the central pier, and at the other locations, since the movement is going to happen in both the directions, this as well as this, we'll have to put the free bearing. Similarly over here, here and here. So all of these would be free bearings. Okay. Now, that was about, how a bearing should be placed. Ideally, for a two-span continuous structure like this with three supports, the pin bearing should be in the center so that the expansion is equivalent on all the sides. Now, you may ask why this expansion is needed or why are we heating up at that location? Yes, the bridge won't heat up at just that one location, but that one location is holding the bridge. So the expansion will happen in all the other directions. Why the expansion will happen? That will happen because of things like temperature loading, your pre-stress losses, and so on. So your bridge, obviously, it's out there in the environment. The temperature variation happens on a daily basis. The top may be hotter than the bottom, and it also happens on seasonal basis. The temperature will obviously be higher in summers as compared to the winter. So all of that leads to different expansion in bridge, and as a result of that, we need to consider these bearings. Just to make a point, it is not absolutely must to go for bearings, but these highly reduce the forces in the structure because of these minor movement, and as a result of that, the structure is very economical. That's the reason why we go for bearings. Now coming to how to model these bearings in the software. So if I want to model the pin bearing, so in that situation, I'll just use the elastic link feature in MIDAS software, which is over here under boundary elastic link. And in that elastic link, I'll give different stiffnesses for different direction. Okay. So my bearing is having only the translational stiffnesses. So only the dx, dy, and dz restraints would be provided. Dx is along the direction of the connection of node 1 and node 2. So the bearing is vertical. So that's why the x represents the vertical direction. So vertically the stiffness will be very high. And in transverse and longitudinal direction, this 3000, that is an equivalent stiffness to represent the stiffness of a free bearing. Because even if I call it a free bearing, if you refer to the IRC codes, the deformation that will happen at that free bearing would be resisted by certain force which is dependent on friction and the applied load. Okay, so these kind of things result into certain stiffness which would needs to be provided for a more accurate simulation of the bridge. Next, if I want to model a transversely guided bearing, so it needs to be free in this direction. So for that, as you can see, the local axis y direction of the bridge needs to move. So that's why at these locations, the SDY stiffness would be negligible. And in case of longitudinally guided bearing, This one, the SDZ stiffness would be negligible, but SDY stiffness would be very high. Okay, so that's how you go about modeling bearings in the bridges. Now, next part. So, as I mentioned, for a bridge structure, it is very common for superstructure, which is the bridge deck, and the substructure, which is the pier, to be modeled separately. Why? Because honestly speaking, at many consultancies, there are two separate teams, two different engineers who expertise in, one will expertise in superstructure, other one will expertise in substructure. So they go for modeling these two things separately. Okay. Whereas in MIDAS, what you can do is you can model the complete structure at once, superstructure as well as substructure. So when you are following the traditional or previous approach where the girder and the pier are modeled separately, so you'd model the girder, you'll apply the loads, you'll provide supports below the girder, and the reactions that you obtain from over here, those would be applied as loads on top of the pier. Whereas in this case, we are modeling the elastic links to represent the bearings and connect the superstructure and the substructure. Now let's have a look at the difference in the results. So these are the bending moment results. As you can notice, where I considered my support below the girder, the negative moment is higher, the negative, that is hogging. The sagging moment is lower as compared to the structure where superstructure and substructure were modeled simultaneously. And this is the real situation, real demand that is going to happen on the bridge, not this. The saving grace for us is the load factors. So 1.35, 1.75, the load factors which we use for a bridge, that accounts for these kind of errors. So this is a simplification. But with today's day and age and technology, I would say this is an oversimplification, and this is what you should actually be designing for, which will give you economical and a safer design as compared to the earlier approach. Similarly, if you look at the peer reactions, excuse me. Okay. So if you look at the bending moment which is coming in a pier, so this is the behavior of a cantilever pier in which very high moment is acting at the top. This moment is obviously equivalent to the moment which is applied over here. And when that moment is acting, this is the kind of bending moment that you would get from the pier. But in reality, with the acting forces, including the redistribution, this is the kind of behavior that you would be getting in the pier. Okay, so now simply assume this as a portal frame. In a portal frame, we know that if a UDL is applied on the top, this is the kind of bending behavior that we will obtain. That is what you would be getting in reality in a bridge as well, and that is something that can be simulated only if you are modeling the superstructure and the substructure together. If we are to compare the deformations, just look at the difference in the magnitude. No doubt, it's a small value. The pier tip top is deflection just about 3 mm when it's modeled separately, and it's about 0.08 mm when the superstructure and substructure are modeled simultaneously. Okay, the magnitude may be low, but the force deformation behavior is completely different. So you should be representing realistic situation as much as possible. Soil structure interaction is actually next step in this part. So below the pier, I had assumed fixed support in the earlier example. But in reality, below the pier, there can be an open foundation, there can be a pile cap and a pile, there can be a well, there are a number of different foundations. And how this foundation is interacting with the soil, that actually governs what the stiffness of the support should be. When you are directly providing a fixed support or something like that, so that's a theoretically rigid support. Now, while that's fine as a basic assumption, that's not realistic. That's where the soil springs or the soil structure interaction comes in. Now, there are two ways to go about it. So one is, say, linear soil structure interaction. So you just decide on one fixed stiffness of this soil spring. You assign that below the pier, and you can go for your complete modeling analysis and design of the structure. Whenever we generate load combinations, those are generally the superpositions of individual load cases, right? And so if you want to sum up the loads, their reactions, and the forces, it needs to be linear. In the next slide, I'll explain how a nonlinear load superposition will give you a wrong result. But the general criteria is you usually go for nonlinear soil spring interaction when you want to go for checking. So all your loads which are acting on a structure simultaneously should be clubbed up in one particular load case, and you should be checking the nonlinear behavior of the structure with just that case. So all the cases would be analyzed separately. Again, we are still dealing with nonlinear springs which are defined in civil itself. But there are other tools out there where you can actually model the soil with its properties. So preliminary analysis of such a structure could be done by exporting the structure from civil to, say, FEA, where you are modeling your soil. You can go for preliminary analysis with certain soil nonlinear material model like Moore Coulomb. And if further optimization is required, you can go for the soil modeling, including all the faults and the variation in layers from a detailed soil investigation report. And you can go for different nonlinear material models like, Hogue Brown or Moore Coulomb. So modified Moore Coulomb and so on. So you can use different material models to come up with a more realistic behavior of the structure. But usually these are used as a check. Okay, so now let's have a look at an example of why you should not be doing load superposition when you are doing, you are considering spring nonlinearity. So the graph on the left, that is representing my soil nonlinear behavior. So it's obviously when I say spring and stiffness, it's nothing but force versus deformation curve. So my spring has a capacity of 100 kilonewton for 5 mm deformation, and for 120 kilonewton force, the deformation would be 20 mm. Okay, so as you can see, the slope is changing after 100 kilonewton force. So let us say we have two loads, one load of 60 kilonewton and one load of 50 kilonewton. So if I am to analyze these loads individually, my deformation would be 60, that is my load, into 5, which is my displacement for 100 kilonewton, divided by 100. So that gives me 3 mm. Similarly, for second load, which is 50 kilonewton, I get a deformation of 2.5 mm. So 3 mm and 2.5 mm for each load cases individually. Now, when I'm going for load superposition, what the software would do is, and again, this is not about the software, this is about how the principle of superposition works. So what would be done is individual results of load 1 and load 2 would be combined. So the total load would be 110 kilonewton and the total deformation would be 3 plus 2.5, which is 5.5 mm. But if I look at my force deformation curve, and if my both the loads are acting simultaneously, the total load is somewhere over here, in which case the deformation should be much higher, right? And that's why you don't do load combination by superposition, but you add both the loads in one particular load case where the applied load is 110 kilonewton and the initial deformation of 5 mm will happen for 100 kilonewton, and for the remaining 10 kilonewton force, the deformation would be based on the updated stiffness, which gives me a final deformation value of 12.5 mm. So just imagine the scale, 5.5 mm is changing to 12.5, and this is the correct one. Okay, so as I mentioned, since loads would be acting simultaneously, they need to be applied in one case, and spring stiffness for each case is calculated individually, so principle of superposition is not valid if they are not combined in the same case. Okay, then the last aspect of this part, different loading requirements. So as I mentioned earlier, for bridge, the loads can be a bit different. The major loads are regular load, temperature gradient loads, pre-stressing, and seismic loads. So honestly, Indian road vehicles are one of the most difficult vehicles globally. And I'm not talking about the traffic condition in India because of which this is difficult. It's about how it has been implemented in the code. So what you see on the left, that is the class 70R vehicle. It's sort of your military vehicle for your tank or your, heavy loaded trucks, something like that. And what is the load and what is the distance between each axle is something which is provided. At the same time, they have mentioned at the bottom in the notes that the nose to tail distance. What is nose to tail distance? The distance between two successive vehicles. The nose to tail distance between two successive vehicles shall not be less than 90 meters for track vehicle, which is this one, and it shall not be less than 30 meters for for wheeled vehicles, which is this one. Okay, so the nose to tail distance for both of these vehicles are different. And similarly for class A vehicle, that nose to tail distance is 18.5 meters. To be clear, that is the minimum nose to tail distance. The code says absolutely nothing about what should be the maximum nose to tail distance. So again, one of the common approaches is the engineers, they give fixed distance between the vehicles, which is equal to the nose to tail distance. But that may not always be critical. So let's have a look at that with an example of influence line. So assume that you have a three-span continuous structure and you are looking for the vehicle position which will cause the worst effect at the mid of first span. Okay, so what you are seeing, the contours on the screen, those are basically the influence line diagrams. So the first span obviously will be having adverse effect. The second span would be having a relieving effect. So because my load is placed on the first span, my second span would be deflecting upward. My third span would again be deflecting downward. Okay, so this is the influence line for bending moment at mid of the first span. So obviously one vehicle would be placed over there for the critical effect. Now, if the nose to tail distance is fixed, then in that situation, the next vehicle would be placed at this location. Now, what happens is when a vehicle is placed at this location, the influence line diagram for vehicle placement at this location would be exactly opposite to what we have over here. It would be something like this. Okay. So what's happening is this vehicle placement is relieving the effect of the load which is placed over here, and this will not be critical. Okay. Let's see if I can just erase ink. Okay, yeah. So this part is done. Let me again just go back to, yeah. So if you put it at minimum distance, it won't give you the critical results. But if you put it in third span, which is much more than the nose to tail distance which is provided in the code, then in that case, the moment would be critical. And based on the code, this is the moment for which you need to design. It is not possible to know this vehicle position without going for influence line analysis. And that is something that is accounted for automatically in Civil NX. The minimum nose to tail distance may not always give the most critical structural forces. You may under design the structure. So please be careful in these aspects. Next is the temperature loading. So as I mentioned before, it can be uniform temperature, it can be temperature gradient. Now, coming to temperature gradient, what that basically means is on a daily basis, the sun will rise, sun sets, and as a result of that, the rays of sun intending on the structure at different times are going to be different. So different temperatures. The top would be much hotter in the day as compared to the bottom. And as a result of that, different temperatures would be acting in different parts of the section for the same cross section. Now, what happens because of that? So let us assume, two different parts, two separate beams. So they are completely subjected to uniform temperature T0 initially, so their lengths would be same. Then they are subjected to T1 and T2, which are different temperatures. So obviously their expansion is also going to be different. E alpha delta T. E and alpha are common, but delta T is different. As a result of that, the strain and the elongation is going to be different. Now, instead of these being two separate beams, if these are two parts of the same beam, then what will happen? The top will try to expand based on the T1, the bottom will try to expand based on T2, and as a result of that, both of these parts would be having a force constraint on each other. And this will result into internal stresses, which are known as eigenstresses. Now, here is again something that we worked on because of the verification that needs to get done. So let me just again switch back to mouse. Okay. Okay, so bridge behavior by V.K. Raina, it's one of the most prominent books which is used quite widely in India, and it's again, it's widely accepted as well. So when it comes to this temperature gradient and eigenstress analysis, a method is proposed in this book for finding out those forces. So this is just a verification calculation for that. I'll just take you through that to give you an understanding of how that works. So in this particular book, the calculation is done for this one problem statement. So this is the cross section of my girder, and this is the temperature variation which is happening in that particular girder. And these are the modulus of elasticity and the thermal coefficients. So in VK Raina, this kind of a plot is given to come up with what is the total thermal gradient, what part is uniform, what part is non-linear, and so on, to come up with the final strain variation which is happening in the structure in the cross section. And for that, certain equations are given for finding out the relations between these plots. So the common method is to apply the temperature based on this and find out the these unknowns. In MIDAS Civil, you input these temperatures in a similar fashion. So how the variation is happening in the top part and what's happening at the bottom. And you will be getting the stress output at all of these locations, which you can obviously view in table at any time. And you can view those graphically as well. And yeah, so when it comes to the method by VK Raina, so the part of the nonlinear temperature which is having that linear variation, so from 30 degrees to 7 degrees, it's a linear variation which is happening, and from 7 to 0, that's again a linear variation which is happening, right? So for that part which is having the linear variation, you can assume that to be one finite strip, and for that you can do the calculations. So this A, Y, and all these calculations are done for this particular finite strip, and you get these values, and you solve the equations which were provided in VK Raina to come up with the final values of the unknowns. And when you use those unknowns to calculate the stresses, so these are the stresses that you get. Now, when you compare the stresses that we got in MIDAS Civil with the stresses which are calculated by the VK Raina method, that's a huge difference. And this is that part that comes in, we were talking about earlier, the manual calculations, right? So this is why it is important. So one of the clients did this calculations and he saw this variation in result. Usually less than 5% is something that you can ignore, but ideally I won't. And in this case, there was one value which was off by 13%. So he immediately got in touch with us, like, what's going on? So we looked into it. Now, as I mentioned, one of the basic things is in VK Arena, the depth of the fiber is considered as 0.25 meter. But if instead of that, I do a manual calculation with the depth of fiber as 50 mm, in that case, obviously the things that I need to calculate would increase. As a result of that, these values would be slightly different. So my unknowns which I will obtain, just look at the magnitude of these unknowns. 2.56 into 10 raised to minus 4, which is not equal to what I was obtaining before, 2.42 into 10 raised to minus 4. It's such minuscule, right? But when you look at the stress output of this, and when you compare it with what we were getting in civil, so now the difference is less than 1%, 0.1%, 0.08%, stuff like that. If you further divide it into strip of 1 mm each, the difference is as good as 0. So the method which is adopted in MIDAS Civil is from a book which is Bridge Deck Behavior by E.C. Hemley, and we can say that is sort of more refined method for the VK Arena. VK Arena method is obviously correct; it's not wrong. The only thing is the engineering assumption of having the bigger finite element strip for that linear variation, that is wrong. That is again one of the most common assumptions that engineers make. So this is something that you need to understand. This is how it works. Manual calculations are needed for understanding that your assumptions are valid or not. And whenever you see a difference, always it should raise a red flag. And always you could get in touch with working engineers like myself or Mr. Bhavin Shah to get these kind of things rectified. Okay, moving back to the presentation. Okay, pre-stressing loads. So yes, pre-stressing is one of the most common loading for bridge, and pre-stressing comes with its own set of challenges. Losses, friction loss, curvature, that's due to curvature as well as wobble, then elastic shortening loss, creep loss, shrinkage loss, and so on. So all of these need to be accounted for. Now I'll play one video in which basically we are comparing again the manual calculation part with the output that we get from the software. Okay, so it's a 7-minute long video. I'll again compare, how the results could be different, and again how it goes down to the manual assumption part.
The precision in coordinate input is best explained with an example. Now, usually when we give out the tendon coordinates on site, basically in the construction drawing, so these are usually at say 0.5 meter or 1 meter distance, right? So let us consider this one girder, which is curved in plan as well as in elevation. And obviously, so the tendon is also having the curvature in plan and elevation. As we can see in elevation, it's curved. And similarly in plan also, the tendon is swaying a bit. Okay, so the same girder and the same tendon profile have been modeled with different precision in input. Okay, now usually when we give it on site, we'll give it in say units. So at say 5 meter distance from the stressing end, the y ordinate is 100 and the z ordinate is something like 500 stuff like that is generally given. So with that in mind, actually the tendon profile is provided in meter units, wherein the x ordinate is considered with 1 meter increment for this girder, 0.4 meter increment for this girder, 0.2 meter increment here, 0.1 meter, and 0.01 meter increment for this girder. So as you can see, in case of this girder, many x ordinates have been given, and accordingly the y and z have also been defined. Okay. Now, if we look at one such definition, so if I look here, so this is the tendon with 1 meter x ordinates. So as you can see, 0, 1, 2, 3, 4, it goes that way. And in y and z ordinates, the precision is up to 6 digits. Okay, so like 234.645 mm. That's the kind of precision that has been considered over here. Okay, so similarly, other tendons have also been defined. Now, when we look at the loss graph, so yeah, the girder is, the tendon is stressed only from one end. So when we look at the tendon loss graph, so for the tendon in which the ordinates are given at 0.01 meter distance, in that tendon, the loss at the non-stressing end or the passive end is, or the force is about 71 kilonewton. Okay, at the stressing end, it is 98 kilonewton and it is reducing to 71 kilonewton at the passive end. And if you look for say 0.4 meter, so at stressing end, it is obviously the same 98 kilonewton, but at non-stressing end, it is 86 kilonewton. So the difference is quite huge, 86 kilonewton compared with 71 kilonewton. For the same tendon profile, if you see something like this, obviously it should ring some bells, like this should not be happening, right? And one may directly jump to the conclusion that the software is not giving the correct result. So in this case, for verification purpose, we have considered, we have generated an Excel file, and we are only dealing with friction loss over here, nothing else. So for the X ordinates, Y and Z ordinates were defined. The change in angle in plan elevation and the actual angles and the change in angles have been calculated. The actual change in total angle, and based on that, the friction loss has been calculated. For the ordinates, the precision was taken up to 5 digits. The calculation is done for 0.1 meter increment, 0.2 meter increment, 0.4, 1 meter increment, and also 0.01 meter. Okay, so for all this, the manual calculations have been done. Okay, and when we look at the total loss result, so when the ordinate is at 1 meter distance, the loss in the friction loss in the tendon is about 11.5%. But when the same ordinate is 0.01 meter, the loss is as high as 28%. Obviously, 11 and 28, these values can't be compared. But from manual calculation, this is what we are getting. Okay. So now, if I change the precision, which is up to 5 digit over here right now, if I change it all, so I'll just replace it. Yeah. 5 with 15. So replace all. And now, so basically this is what I have done. This precision, which was 5 digit before, I have changed it to 15 digit. And now if I look at the losses, so even with 0.01 meter ordinate increment, the loss is about 13%, which is very well in comparison with the other ordinates. Because the reason why this was happening was when you are considering X ordinate at very, very less distance, at that time, if the precision for Y and Z ordinates are not high enough, then the change in angle which is happening between the 2 points is quite high, and as a result of that, the friction loss is quite high. Okay, so when you are dealing with such tendons, just considering close placement of X ordinate is not enough. If you are doing that, then you also need to go for higher precision in the coordinate input. So a simple comparison was made for this. So if you are going just for 2 digit precision, in fact, then you will notice that at the end of 20 meter, that is just one girder, your loss is 100%. So no stress is reaching the other end. That is not right. Similarly, for 3 digit also that was the case. When you go for 5 digit, it was still quite high, but with 15 digit, it was all comparable. But if you notice for the 1 meter ordinate, the difference in the loss values that we are getting is quite low. However, this loss is actually quite lesser than what is expected. So you need to find a balance between what kind of precision is to be considered and what should be the ordinate distance. So having an ordinate distance of say 100 mm or 200 mm, is quite sufficient to obtain good enough loss calculations.
Okay, thank you for being patient for the long video, but that's the point. This bit is about understanding of what happens at the back end. The software is exactly working as it should be working. It's about the kind of input that we had given, the garbage in, garbage out situation. So you need to be careful on how you are working with the software, what you are providing as an input. Okay, moving on.
The precision.
Sorry. Yeah. The next part is seismic analysis. So seismic analysis, again, it can be broadly classified into these categories. So linear static analysis, which is the equivalent static seismic force method. This is generally not used for bridges, especially relatively major bridges. Maybe minor bridge, but ideally nowadays it's always recommended to go for the next option, at least the next option, which is the linear dynamic analysis for, or which is known as response spectrum method. Okay, so the IS, IRC codes all provide the response spectrum based on the site data and the eigenvalue analysis based on which you should be taking the different accelerations and mode shapes and so on. And that is something that can be done with the response spectrum method. Then the nonlinear static method, which is gaining a bit of traction nowadays, which is pushover analysis. So you find out the capacity of the section at the failure, and you just make sure that you know how your failure is happening, whether that is causing minimum damage to the life or so on. So those kind of things could be checked with pushover analysis. And finally, for very important structures which are in highly seismic zone where there have been past records of critical earthquake, or structures like nuclear structures where you need to check for the worst situations. So there you go for nonlinear dynamic analysis, where you consider material nonlinearity, boundary nonlinearity, and so on, and you perform the inelastic time history analysis of the structure. Again, all of these topics are quite wide. And one thing I forgot to mention, the academy data we talked about before, that is for basic usage of the software. But one of the benefits of working with MIDAS is it has been around for a while, since '89, and there are lots and lots of video available on YouTube for learning these things. So chances are, if you just Google, you'll find certain videos where these kind of things have already been explained, and you could freely access those. Okay. The next part, how to determine the tendon profile coordinates. So again, this is a long process, but if I'm to summarize it very briefly, it would be, you just analyze it for your permanent loads and moving load. You obtain the envelope of forces as you see on the right, at what location, what are the maximum hogging and sagging moments. So obtain the required axial force at what eccentricity. So the pre-stressing moment which needs to be applied should be about equal and opposite to the force which is acting on the girder, right? So for that, at which location an axial force should be applied and at what eccentricity from the centroid of the section, you need to calculate that, and that moment would be applied in the opposite direction. So from there, you find out the force which needs to be applied, and then you just find out the number of tendon by this basic formula: required force upon area of tendon, the complete thing divided by the assumed loss, and the permissible yield stress. So the permissible yield stress is something that again you derive from IRC code. I believe it's somewhere like about 76% of the ultimate strength, and that comes to something like 1422 MPa, and that gives you a rough number of tendon as 27. So this force is still for the complete group of tendons acting at the CG. So you need to distribute these tendons in such a way that the CG of all these tendons coincides with the CG of this typical tendon. Okay, how to verify the creep and shrinkage effects, or rather how to assign and verify. So the assignment part is pretty simple. At you go for properties, time dependent properties, you define the creep and shrinkage. Again, you just select the code and give the basic input parameters which are required in the code: compressive strength, relative humidity, notional size, and you can check your creep, shrinkage plots and the compressive stress plots to ensure that the proper values are input. Now, about you know how to assign those. So first part is just defining. Next is actually defining the construction sequence. So in this case, as you can see, as the stage is progressing, the bridge geometry itself is changing. So the load configuration, everything can change. That is one of the major difference between bridges and buildings. The load carrying mechanism, losses, all of that affect what is the force in the structure. And your final complete structure force may not be critical, for which you may need to design. So define the time dependent properties, you define the construction sequence, and in that you activate the elements at different times. So one of the things is, if you look at the dialog box of the construction stage, we have this duration which is in days. Similarly, we have this age which is in days. So what this means is, at the beginning of this construction stage, these structure groups, the elements in these structure groups would be activated at the age of 5 days. So at the very beginning, the age of the element is itself 5 days, and then the length of this construction stage is going to be 12 days. So at the end of this construction stage, the age of these elements would be 5 plus 12, that is 17 days. So that is what this age and duration means. And again, this is very important because the compressive strength of the concrete as well as the losses of the pre-stress, all of that changes with time. Now, as far as the verification is concerned, again, the code provides all the formulations. So, your ultimate creep, the dependence on relative humidity, the factors for that, what those values are based on your site. And then when you compare it to the software, you'd be getting a similar output. So as you can see, for about 100 years with manual calculation, the creep coefficient is 2.869, and you're getting the same 2.869 from MIDAS. Okay, so this is how we could go about verifying it. I have a verification document for it, but I can't go into depth of that right now. We are running out of time actually. Then, about how to simulate the composite behavior in an eye girder. So when it comes to composite sections, the thing that needs to be taken care of, how much section is resisting what loads. So if I am talking about the first stage in which only the girder is placed, so there is only this eye girder which is acting, okay. So obviously its IYY, its stiffness is going to be just for the eye girder part of the section, okay. Next, I am casting concrete for the slab part. So that is a load which is applied on this eye girder. Right, wet concrete has zero strength. So that's why, again, to resist this load, only the girder property would be considered. But once the concrete has hardened and the SIDL load is applied, for this SIDL load resistance, the complete stiffness of the composite girder would be used. Again, you can visit this blog which has lots and lots of knowledge based articles. It's free of cost. You can download the guides and so on. If you want to learn anything about bridge engineering, this is actually one of the good sources to begin with. Now we are getting into the complex part, the buckling and nonlinear analysis. So how to obtain the buckling factors, and what is nonlinear buckling, what are the steps to model a cable stayed bridge, and can we use MIDAS for modeling a stress ribbon bridge. Okay, so these are for the nonlinear analysis. So when it comes to buckling load factors, that is quite easy. Over here we have under analysis buckling load option, where you just give how many modes you want to find, and what is your variable load. So variable load is the load for which the buckling factor would be available. The constant load factor won't have any buckling factor. So you just define that for your pattern loading for which you want to find out the buckling in the structure. Okay, that's it, done. You found the buckling load factor, but this is linear buckling load factor. Okay, So what is nonlinear buckling? Nonlinear buckling is something that you need to consider along with the imperfection in your structure. So again, when you are creating this fabricated structures, there are certain codal guidelines for, how much out of bound a shape can be. And that is something that you can, again, take from there, and you can update the imperfections in the model directly using this option, which is update imperfection. You can select a mode, which will align with your updated imperfection, which in this case was 5 mm. So that imperfection was simulated, and based on that, the complete geometry would be updated such that the node which is most displaced from its position without the first load application is about 5 mm out. And on this model now, you would be defining steel and in this case only steel non-linear properties. So what is the yield stress? What is the material model you want to follow? You define these properties and you assign these to the material. Once that is done, you go to analysis, and earlier we did buckling analysis. Now we would be doing non-linear analysis, and we consider both geometric and material non-linearity. Okay. Now, what should be the load in this case? So in the linear buckling that we did, I obtained certain load factor. In non-linear analysis, you cannot apply a very high load as compared to that critical buckling load factor. Why? Because when it comes to non-linear analysis, it has certain convergence criteria to be met. And this is a bit advanced part. But bottom line is the load application should be about similar to what your critical buckling load factor is. So you just multiply your static load with that scale factor and you up it. And when you apply that, you will realize that in this particular model, my linear buckling factor was 1.27 somewhere over here. But when I'm doing non-linear buckling analysis, the critical load factor is somewhere over here, which is 1.16. So it's generally lesser than the linear buckling analysis load factor. And one of the missing parts in this nonlinear buckling analysis in the codes is they say that the structure should be updated with imperfections, but there is no guideline on how these imperfections need to be implemented or what the magnitude of these imperfections could be. So when you update any model with imperfection, the first mode is obviously the most critical linear buckling analysis mode, but it may not be the most critical buckling mode shape. Okay, so you need to check it with multiple different imperfections, and then you may find out, okay, what's the most critical one. In this case, since this was a simple curve, I am not seeing much variation, but as you can still notice, the curve is not completely coincident. It is varying. Okay, now the next bit is a bit big. What are the steps to model a cable stayed bridge? Uh, Mr. Bhavinsha, would we be sharing this presentation with the people who are attending this session?
Yeah, if you want, definitely we can share it.
Okay, so in that case, because this part is something that cannot be just verbally explained, and that's the reason why I have written a lot of literature in this part. So if you're fine with it, I'll create a PDF and I'll share with you so you can forward it to the
Sure.
attendees.
Definitely, yeah.
Okay, so this what you are seeing here is the complete process of how you could go about generating a basic model for a cable stayed bridge and what all things you need to check. And if you guys need something more on this, we also have a manual and tutorial. Yeah. So again, for those who want to learn, they always have a ways of getting things done. So with MIDAS Civil, you can just get a trial version from the Academy. And when you install it in your system, there are tutorials in C drive with MIDAS Civil is installed. And there we have tutorials for complete modeling analysis of cable stayed bridge. So you can always learn from there as well. There are certain unique features like unknown load factor and cable force optimization or cable force tuning, which need to be used to obtain the final forces in the cable. That is something that you can do over there. Next is the stress ribbon bridge. So what is a stress ribbon bridge? It's basically like a catenary shaped bridge which is made by resting your, say, concrete elements on a stressed cable. So if you notice the image on the right, the cables are stressed, connected at the support, and then concrete is simply placed on it. So this bridge will have a catenary shape. It won't be a straight bridge. That's why it is generally used for pedestrian. Its appearance is quite pleasing. So there is pre-stressed cable inside steel pipes which are not directly connected to the deck, but the deck is resting on it. That makes the deck very slender, and there can be an intermediate support. Now this intermediate support usually won't be a pin support, but it would be a flared support like this again, which would give support in a catenary shape. Okay, so what you see at the bottom, this is a MIDAS civil model for a stressed ribbon bridge without any intermediate support. So it's following a catenary shape with a downward bow. And these are the steps. Again, just model the structure, assume the losses, and from that you do backward analysis. And these are the deformations that you get with, without time-dependent properties. And with time-dependent properties, it comes down to about 65 mm below the originally modeled or required geometry. Now 65 mm below in like 40-50 meter bridge is not bad for the first iteration, but obviously you can go for further iterations to bring this displacement down to 0. And finally, the parametric modeling part that's there in the software. So these are the questions: how can we go about modeling complex geometries, and what can we do? Can we do parametric modeling in MIDAS? So there are two tools. Let me just turn off the ink. Okay. So with MIDAS Civil Annex, we have recently introduced API, and there are many ways in which parameterization can be done. So one of the ways, which is without API, first of all, right now, is to directly use the wizards, and you just give certain numerical inputs in dialog box, and your complete complex geometry would be generated. Next is through use of graphical modeling tools. So one such tool is, say, Grasshopper, in which case you can use Rhino and Grasshopper to come up with your geometry of the structure. And with a very simple code, you can just click on the button and your MIDAS civil model would be updated based on that. So this is something that you could use for preliminary design. Similarly, we have plugins which have come in. Again, there are, I think, about 12 plugins available right now, which you can use for things like generating any alignment, a structure with any alignment, generating series loads, as you can see. So again, for Indian moving load, applying the centrifugal force and all of that can be quite difficult, especially if the curvature of the structure is changing. With this series load generator, the centrifugal force will be calculated in accordance to the radius of the curvature. So even for a transition curve, variable centrifugal force would be calculated and it would be applied to the structure. So these are just two examples of how complex geometries could be modeled and how APIs could be used to further analyze this or load these. Next is what automation is actually available in MIDAS right now. So with API, now the limitation is not with MIDAS, now the limitation is with you. It's totally up to your imagination how much optimization you want to do. So as you can see in the video on the left, we are seeing an Excel template in which, with just a few basic inputs, if I click on update, my MIDAS civil model would be updated with the update required geometry. So the wizard will not generally generate a model which is having cross slope. And when you have used wizard once and you have done other things in that particular model, you can't use the wizard again to modify the geometry. These kind of limitations could be handled with Excel template. Similarly, if you see on the right, that's basically a Python code for how the depth of the section should change so that my final stresses in the section are within the limit. And this is just a very basic example. You can do coding to even go for structural optimization. So initially you may have certain different shape of the truss, and depending on the load which is acting on the truss, the shape of the truss may be completely different, such that the structure is totally optimal. Okay, so that's it from my side. I think we have just about 10 minutes for Q&A, but we can drag it a bit more. That's not an issue.
Yeah. Yeah, okay. Thank you for sharing, very interesting insights about the bridge engineering. Of course, it's a very vast topic, right? So we could not go into much detail about specific area, right?
Yeah.
So there are a couple of questions we received, like, is there any course for design of bridges in MIDAS software?
Yes, absolutely. So let me just, I'll just share my screen again. I'll just show you the Academy website. So that would be a lot easier to explain. Just share my screen. Pardon the internet. I'm actually at a hotel. It's a bit slow.
It's okay. It is just loading.
Yeah. Well, shouldn't take this long. Okay. So as you can see over here, there are different categories for bridge engineering, for geotechnical, for building engineering, and yeah. So and don't worry about these prices. So for all the attendees, you guys just request it on that email address, and we will give you free access to these courses. So the courses are available for Indian code, IRC codes, as well as Euro codes and AASHTO codes for box girder bridges, PSC girder bridges, steel composite, even advanced analysis like rail structure interaction. So all of those things are available over here. As I said, just drop a mail to us on india@midasusers.com and we'll provide you access to these courses. Okay. Mr. Bhavancha, can you see me?
Yeah, I can see. Yeah.
Yeah, I guess I just lost the tab. I have too many things open.
Yeah. Just come to the right tab. In the next tab, you can find us. In your Chrome, in your browser, you just select a different tab.
Yeah, that's what I'm trying to.
Or press Alt tab. You will be able to see.
I think it should be fine. We should continue. What's the next question?
Yeah. Okay. The next point. Okay. Mr. Narayan says that he has seen many videos in MIDAS India YouTube channel that they have used dummy elements for design. So, what is its specific use?
So usual cases where dummy elements are used is mainly for force distribution. So if I am talking about a grillage model, which is having PSC eye girder, so the stiffness of eye girder is very high in the longitudinal direction as compared to the stiffness of the slab which is connecting two girders side by side, right? But these girders are not acting completely independent. Depending on the stiffness of the slab, the force distribution will happen between these girders. At the same time, as I said, the longitudinal stiffness is much higher. So this eye girder is usually modeled with the property of the slab at the top. Okay. So the property of the slab is considered in this longitudinal element. At the same time, I need to model the slab at the same place in transverse direction for that transverse connectivity. So these transverse slabs which are modeled, it will have dummy material, that is its density would be 0, but its modulus of elasticity would be the same as the modulus of elasticity of concrete, so that its stiffness still is the practical stiffness in transverse direction and it will distribute the loads as expected. Another reason why dummy elements can be modeled, and this is a different type of dummy element, would be at the edge of the structure. So if you want to assign certain UDL at the edge of the structure, ideally you don't need any element at the edge of the structure. So you can create a dummy element and you can apply a UDL on this dummy element so that your load application becomes easy. So for these kind of situations, you usually go for dummy elements.
Okay, one more point. Like, can you share the email ID for the courses? You said about one email address.
Yeah, sure. So it's india@midasit.com. Can I type it somewhere?
Yeah, I can type it. India at the rate
India at
midas
midasit.com.
dot com. Okay, I'll just put it that ID in the comment.
Sure, perfect.
Yeah, yeah. Python language generally used in pre or post processing work in MIDAS Civil.
Yeah, that's the thing of the past. Now it can be used for everything. So basically, uh, so let's say you are a hardcore coder. Okay, to open up MIDAS and to perform analysis. Essentially, when we say API and using Python language, it's to send different sort of commands to the software at the backend automatically, so that our life is easier. Honestly speaking, right? So we connect Python with MIDAS with a single key, which is known as the MAPI key. Okay. Now, once this is done, it's up to you how you are coding. You can code it to such an extent that you are using Python on your laptop, uh, but you are working on some other workstation which is lying in a different city somewhere, and your complete thing can be done from your system. So using your Python, you'd be able to generate an Excel design report on your system by utilizing the analysis capabilities of MIDAS Civil NX, which is lying somewhere else on some other system. And it's the complete thing: model generation, analysis case definitions, performing analysis, extracting results, heck, even going for further post processing from that, or running it in loops to further optimize. All of that could be done using Python.
It can based isolator be modeled in MIDAS, specifically about, let's say, damping parameters.
Yes, yes, that's a possibility. It can be done. And again, due to slow internet, it will take me a bit of time in opening up the software, but I'll show where those dampers could be modeled.
Okay.
So we'll come back to this question. In the meantime, can you take up next one?
Yeah, okay. So what are the different types of elements available in MIDAS? Like we talked about plate elements or solid elements. So are there different elements, like different types of shell elements or solid elements,
Yes.
or only unique shell or solid elements?
No, there are different types of elements available. So if I'm to classify it, there is solid, plate, beam, which we talked about, truss, cable, then axisymmetric, plane stress, plane strain. So these are the most common type of elements which would be available. So if we say something like, say, axisymmetric element, that is something that could be used for circular structures which are subjected to circular loads. So if you are having a circular water tank, that is something that you can simulate with axisymmetric element. But if you are having a well foundation of a bridge which is subjected to different moment in transverse and different moment in longitudinal direction, that is not something that you can simulate with this kind of
Hmm.
a axisymmetric element.
Hmm. Right. Okay. Yeah, one question came like, is it possible to show a quick demonstration of, let's say, any small project?
I can show up one of the model. So yeah, first coming back to the damper question, let me just share my screen.
Yeah.
In fact, not just this demo part, I'll also be showing you, rather, if it's feasible with you, I'll be sharing with you a couple of links at a later point, which you could share with the audience. They
Sure.
could see these kind of different project applications and how those kind of things could be done. So I'll just open one of the tutorial projects. So in C drive, so these are the tutorial models which are available. Now, if we look at, okay, so let's look at the cable stage model. I was to show the dampers, but okay, anyway. Okay, so this is one of the, most of the tutorials that we have are made with reference to certain project which has been executed somewhere. So this was one of the bridges which was generated in Korea. And now if we look at, the construction sequence, so let me just turn on few of the other things. So, okay, let me turn off the mask. Okay, of everything. Sorry about that. Yeah, okay. So if you look at the different stages, stage one, just the pylon, then you start the deck casting and you cast the cables and so on. So you would be changing the stages like this to simulate a realistic behavior of the structure. Okay, and now coming to the earlier part, which was about the dampers. So I guess I can just go to the base stage where the complete model is active. And you can go into boundary, general link, and general link properties. So here is where you can see these are the different types of dampers that you could directly model in the software. Okay. So if you are going for something like a triple friction pendulum isolator, so that will have linear stiffness as well as non-linear stiffness. Linear stiffness is something obviously that you use for linear analysis, and for non-linear stiffness you use the non-linear analysis. So this is how a triple friction pendulum isolator should be. It has concave surfaces, and depending on the seismic force which is acting, how it's going to deform, that is something that you can check with the isolator or the damper. Okay, so this is something that you would be modeling in the place of this bearing. So let me just zoom into that part. So this yellow link that you see, that is basically the elastic link or the bearing. And if you want to go for that nonlinear analysis, here you would be making that general link, which would represent the damper property, and then you would subject this structure to the time history or the earthquake load to see the final forces in the structure.
Yeah. The question is how MIDAS is different from CSI bridge.
Yeah, that's a good question. So again, if I am being very honest with you, all the softwares out there are more or less comparable. Someone has some edge over the other. That's obviously going to be there, but there would be no software out there which would be like, hey, this is the only tool you should go for. If I'm being very honest with you, the reason why people have been switching from other products to MIDAS is the service that we provide. Just last month, actually, I had been to California, and if the people would be aware, California is basically the base of CSI. Okay, that's where they're from. They're from, and one of the most advanced seismic engineering group government body, Caltrans, that's from California again. There are engineers over there who have been using CSI for a while, and they have been switching over to MIDAS for the support that we are able to provide them, though we are sitting here in India. So that not knowing how something is being done and not having someone to tell you how it could be done is one of the reasons why people are shifting over from other products to that. Another way in which it's a bit different is now the kind of service that again we are going to provide. With APIs coming in, the kind of development that we can do, it's going to, give out a lot and lot of plugins for localized development. So if I'm dealing about different situations in India, one of the common things is P delta analysis with cracked stiffness, or something like Cloud RSI analysis. So these kind of plugins which makes your life easier are something which are going to come out a lot from MIDAS. So these are few of the basic differences that you could think of.
Yeah. Okay. So that's all.
Okay.
Yeah.
I hope the session was informative.
Yes. Yes. It was very informative. And I think what general feedback, what I'm getting, that we may have in the future discussion on very specific topic. Like let's say we may take one topic and then we have very detailed discussion on. Like when we touched upon buckling. So buckling itself is a very vast
Very
area,
vast.
and there is a concept of non-linear buckling, as you said, right?
Yeah,
Yeah. And even soil
definitely,
stress
definitely.
correction, right? Each topic itself, could take sessions together, right?
Yeah.
Okay, so thank you very much for sharing, quick insights about the questions, whatever we have received so far,
Thank
and
you for
looking forward
providing
to it.
this opportunity.
Yeah, yeah,
Hey,
yeah, and definitely we'll look forward for future. We will collaborate for this kind of sessions, right? And thank you
sure.
all for raising interesting questions, right? Which we could gather, and of course, we could cover only part of questions which we received. So maybe we may be coming up in the future sessions, for covering these sessions. Okay. Okay. So people are saying thank you for the sessions.
Thank you.
Okay.
Thank you for
So
your time.
yeah.
Bye
Okay.
bye.
So now let us stop at this point, and we will meet once again with very interesting discussions. So please
Definitely.
keep following us. So now people are saying, yeah, thank you for the sessions. Yeah. Thank you, Fida. Thank you, Gaurav Vijay. Okay. So we are
Thank you.
signing out now. Good night. Yeah.
Thank you. Good night.
Yeah. Good night.